We're going to make a little tour into the wildlife, and see how systems can help with characterizing the accuracy of reverse GPS wildlife tracking system. So Sivan is going to present this work that was awarded the best paper award at the IPSN conference.
Thanks.
Here we go.
You're going to set up the timer?
Yeah, I'm going to set.
So your introduction made me nervous because it's going to be weird, but I'm not sure it's going to be weird enough for the promises. So these are wildlife tracks. This is joint work with a group from the Movement Ecology Life Sciences Lab in the Hebrew University, Adi, Yotam, Ran Natan, Moti Charter, and with Tony Weiss from Tel Aviv University. And these tracks really start they start with transmitting tags, electronics that are attached to wildlife. You can see here a box of wildlife tags, electronics that we attach or that they attach to wild animals, mostly birds and bats. This box is of small tags weighing roughly 1 gram, somewhere between 0.9 and 1.5 grams. These are bigger backpack style tags with bigger batteries. The electronics is the same, just the batteries and the packaging is different. They get attached to wildlife. These are pictures from a workshop they held last week. There are multiple ways of capturing animals. This is with nets. They're called the mist nets. They get entangled in them, and then they untangle them and put transmitters on them. You can see here maybe the same or another bird. This is called the Bulbul. And the transmitter is being glued with surgical glue onto the bird. It dries out and falls after a couple of weeks. Here you can see a barn owl fledgling, a young barn owl just before he or she starts flying, being fitted with one of those backpack style transmitters. And once you tag enough of them, you see you can get pictures like this. This is these are tracks from 10 hours nighttime, an entire night with 77 barn owls flying in the Hula Valley, northern Israel. The area is roughly, this is maybe something like 10 by 10 kilometers. The system covers an area of about 15 by 30 kilometers, something in that range. What you can see here, the localizations that you can see here, they're about close to 1 million localizations of all the 77 birds altogether. The transmitters transmit every 2 seconds, and on average, we localize one of those animals every 3 seconds. So we lose about 50% of the yield of the transmissions. 50% are not localized, but 1/3 are not localized, but 2/3 are localized. And this is running not for one night. This is running every night. And the 77 barn owls are part of an effort that last week was almost successful. Maybe this week is successful to track all the barn owls in that region. That's completely unprecedented. There are very few cases in which an entire community of wild animals in a region have been tracked simultaneously. And that's what they're trying to do. Last week they still had one female missing. Trying to capture it. Maybe this week it's all of them. And they're doing this because it shows interesting interactions and so on. For example, this is an example of 2 barn owls hunting. It's very close to each other, and you can see completely different behaviors. The blue one has found that a perch, maybe an overhead irrigation line, so it's standing on the perch and then flying out to hunt. The other one has found a field that apparently had a lot of rodents or some other prey, but no perch point. There was nothing to stand, so it kept flying, stitching back and forth, and you can see the boundaries of this agricultural field really fantastically. The fields are, these are old satellite imagery, but the fields are still delineated in the same way. So this one maybe was recently plowed or something, and the other ones had ground cover or no rodents or something. So you know exactly where the rodents are and just kept flying, trying to hunt. So very detailed behaviors. Okay, so that's what the biologists after we are interested in the technology. So let me tell you a little bit about the technology. that's called reverse GPS, and the system itself is called Atlas. We localize a lot of wildlife localization, not all, but a lot of wildlife localization is done using signal measurements of radio signals. The one we all know is GPS. In GPS, there are infrastructure transmitters that are flying out in space. These are satellites. They transmit signals. Your cell phone is a receiver, receives those signals, and by measuring properties of these signals coming from the satellites and knowing where the satellite is, your phone or a tag attached to a wild animal can determine or estimate its position. You can also flip this and use the same math and physics, but just reverse the role of receivers and transmitters, so you can transmit from the unknown location to infrastructure receivers in known locations and do measurements in the receivers, and again use the same principles to localize this. This is called reverse GPS because the role of receivers and transmitters is reversed. There are other systems that use the other localization or navigation systems that use transmitters as opposed to receivers. What do you measure? What properties? People came up with localization systems based on all kinds of measurements. For example, the signal weakens as it propagates, so you can measure signal strength. It's fairly noisy. You get very noisy bad estimates from this. Very popular in wildlife tracking has been to try to estimate angles. So you estimate the angle to the transmitter or to the receiver. You estimate the angle to the transmitter. That's also usually very noisy. There are satellite systems. They're using a satellite system called Argos, for example, which uses satellites receiving signals from terrestrial signals. And because the satellites are moving fast, there is a Doppler shift. You can measure the Doppler shift, and the Doppler shift also gives you an angle to the transmitter, so you can localize this way. Or you can do what GPS does, which is to measure the propagation time. So you measure the arrival time. You need to figure out somehow the departure time. I'll talk about this in a second. And then you use the fact that the propagation time should be equal to the distance divided by by propagation speed. In GPS, it's actually propagation speed is not constant because the signals are delayed in the ionosphere and troposphere. But in terrestrial systems like ours, the propagation speed of radio signals is very constant, very close to the speed of light. So this is really an equality. And it can be very accurate if, and it's a big if you can measure time very accurately. So radio signals travel very fast, 300,000 kilometers per second. So but if you can measure them accurately, you can get very accurate positions, as we all know from GPS, because this equation really holds. To find a position from timing measurements, you need to know both the departure time and the arrival time. We measure arrival times, but we don't know the departure time. The mobile electronics never has a clock that's good enough to really tell you the local time. So in GPS, you don't know the local time. You need to estimate the local time. You know the departure time because the satellites have super accurate clocks. In our system, it's exactly the reverse. Those 1 gram tags don't know the local time. They don't know when they're transmitting, or they know when they're transmitting. They just don't know the time. The receivers have very accurate clocks. So you measure them. So the way you do this, I'll show in a second, is you estimate the departure time together with the location in a simultaneous set of equations. GPS does exactly the same, and you localize. The system, again, there's nothing, just to make sure that everybody understands, it's very simple. It has transmitting tags. The signals are being picked up by radios connected to computers. The radios are digital radios. They digitize a signal, move it to a computer, to basically a desktop PC that does arrival time estimation. These arrival time estimates are sent to a server. The server runs a localization algorithm, solves simultaneous equations, sends the locations both to real-time clients and to databases to be processed later. The results I'm going to show are from a system like this. It's a permanent system, fixed system. We also have a mobile one. It's set up in northern Israel. The convex hull of the system is about 140 square kilometers. It can localize in an area of about 200 square kilometers. That's the map, about, I guess, an hour away from here, an hour and a half away from here. And the location, I should say something about the location. The Hula Valley is both very wildlife rich and very significant to wildlife. It's one of the two main flyways between northern Eurasia, Russia, northern Europe, and Africa. The other one is in Gibraltar, in southern Spain. So basically all large birds need to fly over land. So they fly either through Gibraltar to Africa, or they fly through this area. It's not really a narrows in the same way that Gibraltar is, but there is desert to the east and sea to the west, so they have to fly. There's small birds sometimes cross the Mediterranean overnight, but there are just millions and millions of birds flying over here, stopping over. It's a wetland, it's a historic wetland. Now it's a restored wetland, but it's really an important area. That's why it was worth it to build a complex system and set it up permanently there. Okay, let's talk about how it works. So the equations are really simple. So you can see the circles here, the equations for the circles. T1, T2, T3 are arrival times, or really arrival time estimates. These are the things that the base stations measure, estimate. T is the departure time. We don't know T, but these time differences should be equal to the distance divided by the speed of propagation, as the distance is between the position x1, y1 of base station 1 and xy of the unknown position. Supposedly we have three equations, three unknowns, and you can solve this, and you do get the localization from three base stations. You also get the departure time, which you throw away. You don't care, but you have to estimate it as part of the equations. T1, T3, T1, T2, T3 are really not arrival times, they are arrival time estimates, and they're noisy. And if you have just three equations in three unknowns, you have no idea how large the noise is, how large the error is. So a much better way to set this up, if you have more base stations, and that's part of the reason we put 9 base stations, is to have redundancy so you can average over noise. So you set these equations up and you add a noise term. You don't know the noise. You have too many, or you have more constraints than unknown, and you estimate the unknowns by minimizing the sum of square of the noises of the error terms. Here I'm showing an unweighted. We really use a weighted sum of squares, but that's basically how you do it. This is cheating a little bit, because it's assuming that T1, T is a point in time, and it's assuming that we estimate T1, T2, T3, T4 on some single time reference, UTC, local time, some time, which means that the 4 receivers need to have a synchronized clocks. And really, they don't have synchronized clock. Each one has its own clock. They're all accurate, but they're not perfectly accurate. And synchronizing the receivers is not trivial, and I want to show the non-triviality by showing you the data sheet for the clock we are using. So this it's a GPS, it's called the GPS discipline clock or oscillator. It has 2 outputs. One output tells you the absolute time, and the other output is a clock signal, a 10 megahertz clock signal. This data sheet shows the accuracy. So what it tells us that the absolute clock has an error, a standard deviation, a Gaussian error with standard deviation of 50 nanoseconds, plus minus 50 nanoseconds, which means 50 nanoseconds means that an error of, let's say, 100 nanoseconds, which sounds small, is fairly likely, and 100 nanoseconds is about 30 meters if you translate it. On the other end, the clock output is accurate to within 10 to the minus 11, so which means that over the periods that are of interest to us, the error is equivalent to just a fraction, 1/100 of a nanosecond, which is equivalent to 3 nanometers. So this is very accurate. This is not accurate. the reason is that to get this, to get the clock output to be this accurate, they average over many seconds, and here they don't average. So in principle, it would have been possible to have a better absolute clock, but the clocks that exist are not as accurate. And therefore, what it means is that it means that our base stations need to measure not times, but time intervals. So this is measuring time. We can measure time accurately, but not accurately enough. We can measure time intervals very, very accurately. So that's what we do. We don't rely on absolute clock synchronization. We rely on relative, on measuring time intervals, relative times, and we do this by using beacons. So in addition to these equations, which you've seen before, we now use additional equations, and these equations time the arrival of signals from beacons in known positions. So we have a beacon, for example, B, in position XB, YB. We know XB, YB, we know these positions. We don't know, again, the departure time. We estimate the arrival time, but from this we can extract or estimate these quantities, offset 1, offset 2, which is the clock offset at the different base stations. So we basically estimate, again, it's exactly as in GPS. You have a clock with a good rate, but with a bad absolute time. It has an offset. You solve for the offset. We actually don't, in principle, you can. We have the code to do least square minimization, which is if the noise is Gaussian, sometimes it is, sometimes it's not. You'll see later. Is a maximum likelihood estimation. We use this offline when we recompute localizations at real time. The system localizes wildlife in real time, and we basically subtract equations which produces good localizations, but they're not optimal in the sense that it's not a sum of square. It's not a sum of square. It's not a maximum likelihood estimate. There is another quantity that you need to estimate or eliminate. I just want to mention it, which is the delay from the antenna, because the propagation time you measure is really between antennas, but you don't measure the arrival at the antenna. You measure the arrival of the signal at the analog to digital unit of the radio, and it's gone through 50 meters of cable and amplifiers and filters, and the delay here is about 200 nanoseconds. So the delay here is something like 60 meters at least. You need to worry about this, and it will show up. So. Okay, this is really the most important slide in this talk, because it's an equation or a bound that really drove the design of the system. What it's saying, it's an electrical engineering bound called the Kramer-Rao bound, and what it's saying is if you're looking at the signal, you've received this signal, how accurately can you time this point, the arrival time of the signal? And what it's saying that the best standard deviation, the best variance you can hope for, depends on really two things. It's proportional to the signal to noise ratio. So this arrival time is going to be more difficult to estimate than this arrival time, because this arrival time is of a signal that's less noisy. And if you have higher bandwidth, you have more transitions, it's going to be easier, because the algorithm basically averages over these transitions. So you want to in order to maximize the accuracy of the arrival time, which translates into accurate positions, you need to maximize the signal to noise ratio and to maximize the bandwidth. So we need to minimize these errors in order to maximize accuracy, but we also need to know the statistics of these noise terms. We need to know the statistics both in order to weigh them correctly. So for example, if T2 has a bad SNR and has been measured inaccurately, we don't want to use it, we don't want it to impact significantly the minimization problem. And also, if this one, for example, is inaccurate, this will translate into an inaccurate location, and we want to know how accurate the locations are. So what we do is we estimate this term, we measure the SNI directly, and we estimate offline this term in order to get an estimate of the arrival time accuracy and the position accuracy. And it seems easy, you just collect samples and measure, but the problem is that you can't collect samples because you can never know what the actual error is. You can't measure one of those errors because you don't know the departure times. So what we do is we've developed a scheme in which we measure the time difference. We use two base stations, one transmitter that's transmitting repeatedly. We measure the time difference between two reception events in one base station, in a second base station. They should be the same, so we subtract them, and the difference is a sum of 4 errors, so we get statistics of sums of 4 errors, and we extract the data from there. So this is the fit, and here this is a really fantastic graph. You can see here the Kramer-Rao bound. So you can see that as the SNR becomes worse, the error starts to spread out, and you can also see that at high SNR, something else that's not the Kramer-Rao bound really prevents the error from going really down, and that's the errors in the signal that's being transmitted. It's not accurate enough. The clocks are not accurate enough, so there's some stuff here that you can see that's not the Kramer-Rao bound, but this is in this range. The errors are in the single nanoseconds, so they're really small. Okay, there were some technicalities in producing the position estimates. It requires some hairy calculus. I won't go over this. How accurate is it? So these are clouds of localizations from a beacon that was used, that were, the localizations have been computed using another beacon, a separate beacon at a different location as a time reference. You can see 2 clouds of points for 1 hour at 2 different frequencies. The beacons were transmitting at 2 different frequencies. You can see a Gaussian cloud, which is expected, but you can see that the clouds, this is 0-0 error, that the mean is not 0. Even here it's about 5 meters, here it's about 15 meters, and it's weirdly frequency dependent. It's probably frequency dependent because of those analog delays that are different at different frequencies. So this is 1 hour, and if you take this and compute the statistics of these 2 clouds for 1 hour, and you repeat this for an entire week, that's what you get. So the standard deviation, which is here, remains around 5 meters, so the spread is roughly similar to GPS. The mean error is larger, also not very different from GPS, on the same order of magnitude, but and frequency dependent. But you can see that it's moving slowly, so you can subtract it, you can account for it, at least to some extent. And the other thing you see here is that the yield, there should be 1,800 localizations per second per frequency, and the numbers are really very close. There was at least some periods in which there was some high interference that was probably also not Gaussian, some strong transmitters, so you can see that the errors are larger, the mean error is larger, and we also got fewer localizations during those times. Now the cool thing about, one cool thing about the paper is about that we've been able to get similar statistics, but not for beacons, for transmitters on plastic poles, but for what actually you get on wild animals. And the reason we could do this is because we used barn owls, and while they incubate or they have small chicks, the females remain in nest boxes, so you know where they are to within 15 centimeters or 30 centimeters, so you have ground truth. So we localize wild animals while having ground truth. This is really cool. And you can see that the errors, so this is just during the day. We don't show you the data during the night because we don't have ground truth during the night. So the errors are similar. The standard deviation is similar. The mean error is slightly larger, but on the same order of magnitude. You can see that the yield is much more variable, but still hundreds, sometimes more than 1,000 localizations per hour, which translates into what I showed before, 1 every 3 seconds during the entire night. The covariance is indicative. It's not accurate quantitatively, but it's accurate qualitatively. I'll move over. This is a track of one owl, and you can see the different behaviors because of different interference environments. So you can see it was flying out, and blue and green means small covariance, highly accurate localizations. And then on the way back, some interference kicked in, so you can see we have fewer localizations than they're red, which means that the estimate is more noisy, and you can clearly see that they're more noisy. So this, for example, is the estimate is 1.4 meters, and it's an average of 4 base stations. This one over there is an average of only 4 instead of 7, 4 base stations, and the estimated standard deviation is 24 meters. You can clearly see that there is a correlation between our estimates and what we get. The system is complex. I won't go over it. It's complex, has many different components of completely different kinds. Databases, DSP, those miniature embedded systems, and it's running 24/7 for more than 2 years, which means that all the glitches and quirks and all of those components have shown up. The biologists have tagged over 300 individual animals, 22 species, a lot of birds, 2 different bats, and they're able to do this because the tags are really, really cheap. They cost about $25 each, as opposed to GPS devices for checking wildlife, which cost somewhere between 500 and 3,000 bucks. The amount of data that we produce, this is the graph. We now have, you can see the rate is going up, and we have over 200 million localizations produced by the system. The entire research world has produced 250 localizations using GPS technologies and satellite Argos localizations in 4 years. So we are now producing every 3 or 4 weeks a number of localizations that's been produced by all the other groups together in a year or so. The yield. And another very important thing that took me maybe a year or 2 to understand how important this was to the biologists is that it's not only that we can collect a lot of localizations, we can collect localizations for a lot more species because the tags are lighter. So most species of animals of all kinds, birds, mammals, and so on, are light. You see this distribution of weight mass in all types of animals, and with GPS you can tag about 40% of the animals. With our system or systems like ours, you can tag about 80%. They're all moving down, they're all becoming lighter, but it takes time. The high-level message is that, I mean, it's fun to be a computer scientist because we see computing transform our societies, transforming good ways, bad ways, but computing is really a strong transformative power. It's also obviously transforming science, but there is a difference between science and other applications like consumer and medical, and that is that corporations and startups are not that interested in advanced computing for science, and that creates incredible opportunity for academic researchers to make a really interesting impact. So join us both in the broad sense. I mean, this is clearly not new. In bioinformatics, people have been doing this. In the broad sense, looking for opportunities to make an impact through computing in science, and also in the local sense, if people want to join, you're welcome to join. Okay. 2 of the co-authors.
Time for 1 quick question. Well, keynotes get more time apparently, but yeah.
I wanted to see the species graph that you had. The yield graph, yeah, yield by species.
The yield by species. So on beds we get about 50%. On beds about 30%. But even it's not that informative. These are cranes, for example, we got about 10%, but that's because they stay on the ground most of the time. So we get clouds of point where they're in the pond, they're standing, trying not to be eaten. When they fly, you see wonderful tracks. So when they fly, we probably get 90% of the points. When they're on the ground, there are ground reflections. There is strong attenuation of signals coming from low transmitters.
Thanks. So it already answered my question then, why it's not applicable for navigation within a building then?
You need a lot of infrastructure points. I mean, in IPSN, for example, navigation inside buildings is one of the hottest topics in sensing. There are many techniques that are better than this. This is part of the answer is part of the reason that there are opportunities for computer scientists to make an impact, and this opportunity has been out there. I mean, we are the second system. There was also a really pioneer system for Cornell. Because I think we had this opportunity because it's not useful for humans. So humans can carry phones, we can carry GPS devices, we can charge them at night, and so on. So all of these properties make GPS very attractive. And this technology, I mean, the physics, the math, the idea is not new at all, but it really has apparently very few consumer applications. So nobody produces this.
Right.